Hi, everybody. It's Professor Mitchell. Continuing with Chapter 8, today we'll be looking at Section 8.4 on trigonometric substitutions. So the idea behind trigonometric substitutions, they are generally used for integrals containing expressions like the ones you see here, the square root of a squared minus x squared, the square root of a squared plus x squared, and the square root of x squared minus a squared. We will be using our Pythagorean identities in the following forms. 1 minus sine squared theta equals cosine squared theta. 1 plus tangent squared theta equals secant squared theta. And also secant squared theta minus 1 equals tangent squared theta. All right, so it turns out that you can often make these integrals a lot simpler into an integral that you recognize how to do by making the following substitutions. If your integral contains an expression of the form square root of a squared minus x squared, you're going to substitute x equals a sine theta. Now, in order for this substitution to work, theta needs to be in the closed interval from negative pi over 2 to pi over 2. And that's because we need the inverse sign to exist. Okay. Most of the time, you don't have to think about these restrictions. Definitely, if you're dealing with an indefinite integral, you don't have to think about them. You may have to think about them if you're looking at a definite integral. All right, for the form square root of a squared plus x squared, make the substitution x equals a tangent theta. And that substitution is good for theta in the open interval between negative pi over 2 and pi over 2. And finally, if you have a square root of x squared minus a squared, you're going to substitute x equals a secant theta. Now, this one's a little bit more complicated, but the way that your textbook deals with it is they say that they're only going to deal with the case, and I don't have a mouse at this moment, but you can see in the lower right corner of your screen where it says provided x over a is greater than or equal to 1. Then this substitution will work as long as theta is greater than or equal to 0, but less than pi over 2. All right. If x over a is, forget if it's less than or equal to 1 or less than or equal to negative 1, then you have to look at theta being in a different interval. But we're not going to worry about that. All right. So really, just like with a lot of other things, I think you'll really start to pick this up when you start to see the examples. But at a certain point in all these problems, we will be drawing a reference triangle, and that will help us put together the pieces of the new integral. Notice on each of these triangles, the square root expression simplifies to something with an absolute value in it. As long as theta is in the intervals that I was showing you on the previous slide, then the corresponding trig function will be greater than or equal to 0, and you don't have to worry about those absolute values. All right, so the procedure is as follows. This is the procedure that you'll see me doing in the examples. First, write down the substitution for x, calculate the differential dx, and I would say if it's a definite integral, then specify the selected values of theta for the substitution. If it's an indefinite integral, we will not worry about that. Second, substitute the trigonometric expression and the calculated differential into the integrand, then simplify the results algebraically. Next, we'll integrate the trigonometric integral, keeping in mind the restrictions on the angle theta for reversibility. And finally, we'll draw an appropriate reference triangle to reverse the substitution in the integration result and convert it back to the original variable x. All right, so these are the examples that we're going to be looking at. So now I will switch over to the tablet and we will get to work. All right, so here's our first example, the integral of 1 over 4 plus x squared to the power 3/2 with respect to x. Notice there is no square root symbol in here, but remember that 3/2 power is a type of square root. It means the square root raised to the 3rd power. So we can still use the substitutions that we were just talking about. So this one is the most like the form square root of a squared plus x squared. So the substitution for that is x equals a tangent theta. In this case, a is 2 because a squared is 4. All right, so we're going to let x equal 2 tangent theta, which is going to make dx 2 secant squared theta d theta. All right, so now we have to make sure that all of the pieces of this integral are in place. So now let's talk about 4 plus x squared to the power 3/2. That's going to be 4 plus the square of 2 tangent theta is 4 tangent squared theta. All right, so now what I'm going to do is factor out this 4. Remember, the 4 is raised to the power 3/2. So that's going to be 4 to the power 3/2 times 1 plus tangent squared theta to the power 3/2. All right, and this is the reason that we use this substitution. Because of having that a squared plus x squared in here, you're going to get a 1 plus tangent squared theta, which you can then replace with secant squared theta. 4 to the power 3/2 is 8. And then secant squared theta to the power 3/2 is just going to be secant cubed theta. All right. So that was a fair amount of work. It's a little more work than your basic U substitution. Let's see what this is going to do to our integrals. So dx has to be replaced with 2 secant squared theta d theta. And then 4 plus x squared to the power 3/2 gets replaced with 8 secant cubed theta. All right, so now hopefully you see nice things about to happen. 2 over 8 is 1/4. Let's put that out front. And then secant squared theta over secant cubed theta is 1 over secant theta, which of course I would rather think of as cosine theta. All right, nice simple example to start with. Yes, this would be considered a simple example, all right? Because the integral that you get in terms of theta is one that is super easy to evaluate. That doesn't always happen. All right, the integral of cosine theta is sine theta. Okay, but now we have to put this integral back in terms of x. So let's do that on the next page. And this is where we use our reference triangle. So remember that x was 2 tangent theta, which means that tangent theta is x over 2. So if I draw a kind of sloppy right triangle, starring the angle theta, by some old hippies came around here tripping on acid, tangent is the opposite over the adjacent. So this would be x, this would be 2. And then by the Pythagorean theorem, the hypotenuse squared would be 2 squared plus x squared, which means the hypotenuse is the square root of 4 plus x squared. All right, so we had found that that this integral in terms of theta came out to 1/4 sine theta plus c. Well, the sine of theta would be the opposite over the hypotenuse. So this is going to come out to 1/4 times x is the opposite over the hypotenuse is the square root of 4 plus x squared. And that's a perfectly fine answer. For some reason, I'm feeling the need to write that as x over 4 square root of 4 plus x squared plus c. I think these are kind of fun, but of course I would, right? Okay. All right, let's look at the next example. This is a definite integral. Now, you've seen me many times convert the limits of integration when I use, regular old U-substitution. I don't always do that with trig substitution. I really don't think it saves a whole lot of work. So what I'm going to do probably is just pretend that this is an indefinite integral. I will change it back to x at the end and then just plug in the original x limits. All right, so this integral involves a form square root of x squared minus a squared. And that's the substitution that uses secant. So let's let x equal 4 secant theta. Since this is a definite integral, let me just point out that because x is between 4 and 8, and x and a is equal to 4, that means that x over a is indeed greater than or equal to 1. We mentioned that at the beginning. So we are thinking of theta as being between 0 and pi over 2. Okay, greater than or equal to 0, but strictly less than pi over 2. But again, I'm not going to change my limits of integration, so we probably won't have to think about that. Okay, so if x is 4 secant theta, that means that dx is 4 secant theta tangent theta d theta. And now let's talk about the square root of x squared minus 16. All right, if x is 4 secant theta, that means x squared is 16 secant squared theta. So now if I factor out 16 and bring it outside the radical, it's going to become a 4. All right, and again, you see why we use this substitution, because now we can change secant squared theta minus 1 into tangent squared theta. All right, and this is one place that restriction on theta really comes in. We mentioned not too long ago, just a section or two ago, that in general, the square root of u squared is the absolute value of u. So if I didn't know anything about theta, the best I could say is that the square root of tangent squared theta is the absolute value of tangent theta. But because theta is between 0 and pi over 2, that means the tangent of theta is positive. And we can just say that this is tangent theta. I am going to put a note on here. Since 0 is less than or equal, theta is less than pi over 2. Okay. All right, so now let's build this integral back up. Again, I am going to pretend it's an indefinite integral just for the time being. Okay, so the integral x squared, square root of x squared minus 16 over x dx. The square root of x squared minus 16 becomes 4 tangent theta. X is 4 secant theta. And dx is 4 secant theta tangent theta d theta. Okay, and then what usually happens at this point is that you can cancel out a bunch of stuff. We can get rid of these secant thetas, get rid of a pair of 4s. And then what we're left with is 4 times the integral tangent squared theta d theta. All right, now I remember sort of indirectly referring to this integral in the last section. I remember that one of our problems involved the integral of cotangent squared theta. And I mentioned it was just like the integral of tangent squared theta, which I mentioned that you had hopefully done in Calc 1. The way to deal with integral tangent squared theta is to change your tangent squared theta. I don't know why they're after me. I did not divide by 0. Into secant squared theta minus 1. Because that's something I know how to integrate, right? The integral of secant squared theta is tangent theta. And the integral of 1 with respect to theta is theta. All right, so now we'll go on to the next screen and we'll draw our reference triangle so that we can write this back in terms of x. Okay, so the original substitution was x equals 4 secant theta, which means that secant theta is x over 4. All right, now some old hippies came around here tripping on acid. Does not talk about secant, but it does talk about cosine. So if secant theta is x over 4, we know cosine theta is 4 over x. 4 would be the adjacent, x would be the hypotenuse. All right, that triangle looks a little better. So if this is theta, then this side would be 4 and this side would be x. And by the Pythagorean theorem, x squared would be equal to 4 squared plus opposite squared, which means x squared minus 16 is equal to opposite squared, which means opposite is the square root of x squared minus 16, right? Okay, so in terms of theta, this integral came out to 4 times tangent theta minus theta. All right, so tangent theta is the opposite over the adjacent. So that would be the square root of x squared minus 16 over 4. All right, now this is something that happens every so often. What do we do with just plain old theta? Well, we go back up here. Since the secant of theta is x over 4, that means that theta is the inverse secant of x over 4. And that's what we're going to fill in for theta. Inverse secant of x over 4. All right, now we're not quite done. We're almost done. Remember, this was a definite integral. Okay, so I'm glad I left 3 pages. So it was the integral from 4 to 8. Oops, that's a funny looking 8. And what was it again? It was the square root of x squared minus 16 over x. Okay, so we've got our antiderivative for the square root of x squared minus 16 over x. That is 4 times square root of x squared minus 16 over 4, right? Minus the inverse secant of x over 4. So now we'll plug in 8, plug in 4. All right, so that is going to give us 8 squared is 64. 64 minus 16 is 48. Minus the inverse secant of 2 minus 4 squared is 16. 16 minus 16 is 0. Minus the inverse secant of 1. All right. So what is the inverse secant of 2? Well, it's the same thing as the inverse cosine of 1/2. So think about your unit circle. What angle in, technically I should say, well, no, it would be quadrant 1 because we're assuming that theta is between 0 and pi over 2. So what angle between 0 and pi over 2 has a cosine of 1/2? Well, it would be pi over 3, right? Let's see. So this is 4 times, and let's see, I guess I should simplify this radical. Square root of 48 is 4 square root of 3. Minus pi over 3. Okay, and now we can just ignore this 0 and say plus the inverse secant of 1. The inverse secant of 1 is the same thing as the inverse cosine of 1 over 1, which is 1. The inverse cosine of 1 is 0, right? All right, so that's our answer. Let's see, how should we write this? Well, we could get rid of these 4s, but then we're going to pick up the 4 that's outside. So I would probably write it as 4 root 3 minus 4 pi over 3. That's so much fun. I love it. All right, example number 3, or letter C, I should say. Okay. Hopefully you can guess what's going to happen here first. The integral of the square root of 1 minus the square of natural log x over x natural log x. So we're going to do probably 2 substitutions in this problem, and we're going to start with our regular old friend U-substitution. So let's start by letting U equal natural log x, which of course is going to make du 1 over x dx. All right, so this is going to give us the square root of 1 minus u squared. And now notice that dx over x is going to turn into du. But I do have another natural log x in the denominator, and that has to get replaced with u. Now, this looks a little bit like the one we just did. Unfortunately, it's not quite enough like the one we just did, because the one we just did was a different form. It was square root of x squared minus a squared. This one is square root of a squared minus x squared. All right, so this is the other substitution. And I'm sure when I first picked these examples, I picked them so there was one of each. All right, so now we're going to do another substitution. This is going to be our trig substitution. we're going to let u equal, in this problem, a is 1, right? So u would just be sine theta, which is going to make du cosine theta d theta. And the square root of 1 minus u squared is the square root of 1 minus sine squared theta, which is the square root of cosine squared theta, which, because of the restriction that we're assuming on theta, is just going to be cosine theta. All right, so I think we have everything we need. The square root of 1 minus u squared is cosine theta. U is sine theta. And then du is cosine theta d theta. All right, so what are we going to do with this integral? Nothing cancels out right off the bat. So what we have here is the integral of cosine squared theta over sine theta. So this would probably fall into that miscellaneous category from the last section. I think the thing to do here is to rewrite cosine squared theta as 1 minus sine squared theta. And then we're going to do this as two separate integrals. So the first integral is going to be 1 over sine theta. And the second integral starts with a minus, is going to be the integral of sine squared theta over sine theta, which is just sine theta. All right, so this shouldn't be too bad. 1 over sine theta is cosecant theta. The trick for integrating cosecant is very similar to the trick that we used way back in chapter 7 for integrating secant. I am not going to reinvent that trick. I'm just going to get it off our section 8.1 formula sheet. All right, so that is formula number 15. The integral of cosecant theta d theta would be negative natural log absolute value cosecant theta plus cotangent theta. And then, of course, the integral of sine theta is negative cosine theta, and we have a minus in front of the integral, so that's going to give me plus cosine theta. All right, so now the next thing we get to do is put this back in terms of u, and this is where we're going to use our reference triangle. So remember that u was sine theta. Think of that as u over 1. Sine is opposite over hypotenuse. So this triangle is going to look something like this. The opposite would be u, the hypotenuse would be 1. The missing side is the adjacent. And just to save a little time, I'm going to, you've seen me do this twice before. Pause the video and try to do it yourself if you're not sure, but the adjacent is going to end up being the square root of 1 minus u squared. So that means that this thing here, well, let's see, before we start writing everything down, let's put the correct ratios in here. So cosecant is the reciprocal of sine. Oh, that's just going to be 1 over u because sine theta is u over 1. All right, cotangent is going to be the adjacent over the opposite. The adjacent is the square root of 1 minus u squared. The opposite is u. And then the cosine of theta, that's the adjacent over the hypotenuse. That's going to be the square root of 1 minus u squared, period, plus c. All right, now I'm looking this over, trying to see if there's really any way to pretty this up. Well, I mean, you could combine these two fractions. You could also do away with the minus sign here by flipping the fraction over inside. In fact, I think I'm going to do that. But I want to stress to you that I don't want you to get aggravated about trying to write these answers in their prettiest form. Your online homework program is very good at recognizing, you know, answers that are maybe not simplified quite to the point that they would have. But I like to do it. All right, so, but let me not skip any steps here. So first I'm going to combine those into one fraction. So that's going to give me negative natural log absolute value 1 plus the square root of 1 minus u squared all over u, right? Plus the square root of 1 minus u squared. All right, and then using the property natural log 1 over x is equal to negative natural log x. If I flip that fraction over inside, then I can lose the minus sign in front. Okay, so we'll have natural log absolute value u over 1 plus square root of 1 minus u squared. All right. I would have remembered the plus c at the end. All right. Okay, so now we have to put this back in terms of natural log x. Remember, u was natural log x. Okay, so this is a kind of ugly answer, isn't it? It's going to be the natural log of the absolute value natural log x over 1 plus the square root of 1 minus the square of natural log x plus the square root of 1 minus the square of natural log x. And no points if you don't remember the plus c. Just kidding. All right. One more example. Okay, so at first glance, this looks like a let x equal 2 secant theta. But I always like to throw in a problem like this to emphasize the point. If there is a simpler way to do it, you should do it the simpler way. This x sitting out here actually means that there is a much simpler way to do this problem. This is just a regular old U-substitution. This is a Calc 1 problem right here. Regular old substitution. Just let u equal x squared minus 4. That's going to make du 2x dx, which is almost exactly what I want, except for the 2. And voila. This integral is just 1/2 integral u to the 1/2 du. It's a regular old backwards power rule. All right, the integral of u to the 1/2 is u to the 3/2 divided by 3/2. Dividing by 3/2 is the same thing as multiplying by 2/3. All right, so this one just comes out to 1/3 x squared minus 4 to the power 3/2 plus c. No trig substitution needed. Right, so do be on the lookout for those. And that's going to do it for section 8.4. We'll see you next time.